to do something.
Private wire protections, or in other name for them, differential protections. Who they are and why we are interested in them. Idea. Let's see, we have something to protect. Possible or powerful from both sides. Here is our protected object. What can we do? We can plant a current relay like this. Yeah, everything. Repeat it once more. Okay, here it is, my pattern of current relays. Let's take internal fault and external fault. In case of an internal fault, we will have current 1 and in blue current 2. In case of external fault, only current 1. External fault. Here, one current and second current. What will be current through relay? Approximately double fault current. What will be current through here? One. And what about this one? Current is approximately 0. Here, current to relay is approximately double current of fault, approximately 0. What can we tell? This kind of protection buildup ensures very high sensitivity. Should be pair of contacts for to switch, but it's highly sensitive. And one more, it's absolutely selective. Overcurrent protection, distance protection, rely on relative selectivity. Selectivity, how to say, achieved with different operation current and, what important, with delay operation, with time delay. Here we have absolute selectivity and instant operation. One only problem, we need way to supply current of the opposite side to our protection device. promising scheme. I need to manage one thing. This kind of protection, it's very lucrative to reduce it. Use reduced version. See, in case of internal faults, currents are oriented towards fault place, in external point outside. One of the way of development of such kind of protection, differential. Here, inverted the differential isotype, these protections are called differential because key elements operate on current difference. In English terminology, they are often called pilot wire protection. I will explain it later. But no, this kind of protection, it appears very, how to say, promising to reduce it to so-called differential phase protection. Protection of phase difference. One moment, I will explain kind of reduced branch. Idea, protected object, bus box, current sensor, bus box voltage, transformers. Idea is to use power direction function. Current, voltage, current. To use power direction function. In case of external fault, or maybe in case of internal fault, we will see power flow towards fault place. So, if I have for these relays characteristics like characteristic to 3, if power from bus towards load, in case of internal fault, both will show positive 1 and appears, and I need disconnection switch, these are circuit breakers. If both power direction relays show 1, meaning what we have in flow, disconnect the object. Will this work? No. Why? If I start something like this, to implement in reality something like this, all these elements, they do have internal capacity. In the no-load regime, there will be flow towards these capacities. And protection will operate falsely. To prevent this, I need to implement current limiting function. Otherwise, this protection will falsely operate in no-load regime. prevent misoperation in no-load regime, I'm forced to limit with I need to limit it at last at load current. And what will happen? In normal load regime, everything will be fine. But if we are in situation where this source is not available, protection will fail. Because, I took any source, this source may be disconnected. Protection will fail because there will be no current to operate at this site in case of internal fault. So this kind of protection, it operates instantly. It appears safe, but it's not reliable when one of the sources is disconnected, because it's mandatory to have current threshold. If I am without current threshold, it will still be unreliable, because without current threshold, this element can operate failessly from the noise. So these schematics appears to be good. It's repeated multiple times, but it's not so reliable as it appears. There is, I saw versions where what was done, in case this side trips and here is zero current, it disconnects both switches, but it's not a very good solution, really. Yeah. Version based on power flow isn't reliable. It should be combined with something more. It can be fixed for power line, but I strongly recommend not to use it for the schematic for protection of transformers or generators. Okay, let's go forward. Assume we have source, bus, switch, my protect object net switch, come on, something very simple. Current relay. Current transformers, very nice. And we have what, let's assume that system 1, for example, cells and to system 2, something like this. Or maybe external fault occurs. Where do we need to look? This transformer, it can be any current sensors, but okay, let it be transformer. These transformers are real. Ideal transformers do not have error. But real one, yes, they have error. I can repeated. Real current transformer have it magnetizing charge. It's induction in quark from MTS. Primary current, primary current, secondary current. For ideal transformer, it should be straight line. In reality, because of saturation, we will see something like this. Independence of load, saturation, 10% error point moves, but anyway, it's a real thing what we see. So, error of transformer we will see something like this, group of error. In our case, error itself, it's not a giant problem. Problem, what we have outside load, outside fault, current going through. Let's say if load, current goes through. In ideal case, should be 0. In reality, it's a so-called non-balanced current. It's a current caused by error characteristic of real current transformer, any current sensor. Has something like this, only knee point moves. Best sensors will have it far away, but somewhere this point exists. We see if our relay has a fixed trip current, it sets somewhere is a limiting point of sensitivity. We need problem. If we deal with transformer protection or generator, we need to sense interwinding faults, and they are characterized with change in current less than %. At early stage, fault, the difference in case of fault, interwinding fault, will be less than %. We need highly sensitive relay. This flat version will not work. We need something better. Problem what operation current of this relay, I just draw some simple relay. In reality, this operation current, we need, in ideal case, we need something with safety margin from the error characteristic, non-balanced current characteristic of our current sensors. We need, in ideal case, it should be adaptive. So E trip should be function of load current. Otherwise, we will suffer from significant loss in sensitivity. it's a problem. Interesting. Can I do it? 1 second. I will try to show problem number 1. Number 2, sorry. Maybe I will be able to do so. Maybe not. There is another problem. Where are my keys? Yes. 1 second, I will get my picture. One day I will kill this TV. Yeah, this bit better. No. Yeah, here it is. Maybe on B phase. It's phase A. Here is B phase. This connection. Yeah, something like this. You see it? Yeah, it's visible. It's a magnetizing current of transformer or inrush current. Inrush current from my small transformer. What happens? See, at the moment transformer is energized, there is no magnetic flow in the core. Since there is no magnetic flow, nothing in this nice box self-induction EMF on primary winding will be nothing. Or maybe this one. Single try for the A phase. Nice, isn't it? And it's not sine. It will become a sine later. But at the starting point, you see, it's not sine, and it has huge exponential component. Inrush current, in the moment first switch operates, we will see this one flowing through our protection. Problem of inrush current. If you do nothing, your protection will falsely operate, because this current exists on the primary side, but there is no such current outside. It's not outflowing. This current is going inward. Yeah. Maybe you can think on solution, what to do, delay operation. Just delay operation till the transient ends. It's a very bad idea, in my opinion. Because the higher, if you look on probability of fault, the faults are probable when, if we speak on transformer, transforming winding is subject to mechanical force. When these forces are on the top, near short fault. But also inrush current, this jump of magnetizing current, is the moment when windings are subject, they're trying to mechanical force. It's the moment when interwinding fault is possible. We need to operate safely. To operate safely, what we do? We need operational protection. But this protection should not operate falsely from inrush current. It's a problem. We need to face problem. How? See, two problems, and we need to tackle both. Is my we need to do something. Railway, come here. This is interesting part. It's inner transformer. This kind of electromechanical relay still operate, especially you will find them in power plants where they came in original supply. Operators are very reluctant to replace them. Here. Version. Differential relay with magnetic braking. See, put it here. With another version. But again, if you look inside, you will see three-leg transformer, and here, can you see it's in the gap between terminal boards. It's transformer with interesting design. It has reduced number of steel plates in the core. Achieve this, for example, winding, and holes can be drilled. What it gives? It will create saturation areas here, where these are with them saturation area is creating by reducing number of plates of the steel sheets. These holes can be achieved simply drilling holes to create areas of saturation. How it works? One second. And which one? Oh. Let's take this one. Okay. Idea. Thin leg, wide and thin. Here in this area is separatable. Here, railway coil. To be able to set 3-point shunting resistance is added. It's for setup. This one is number 2. This one is operational. Differential current flows through this winding. And relay also has this short-circuited winding. Some versions have additional adjustment resistance. Saturatable. How it works? Strange thing, isn't it? It's a compact design, but to analyze, we can split it. See, this central leg is made wider, and its magnetic resistance is much lesser than side legs plus saturatable areas. So we can separate this transformer into analysis can be performed easy if we separate real transformer into assume it is a pair of two ideal. It's like cutting in the middle. This one will be saturatable, and this one is normal. Saturation areas. Yeah. Secondary windings with 3-point setup resistance in opposite zone. Differential current inflows, differential current outflows, magnetizing flux will be directed this way, and I assume this is flux from my differential current. Fine. Maybe. Okay, for simplicity, I have binding here, here, and something like this. Interesting is this flux. It's from current in the loop. Here, this flux and this flux will initiate current in the loop. You can plan resistance, but it's not necessary, real. We also will get this kind of flux. Idea how it works. You see two opposing flux in normal transformer and in a saturatable transformer. See the idea. Assume we have normal regime, no exponential components, current just flowing. If current just flowing, what we will see? White flux. White flux comes this way, transforms, and as a result, here in loop circulates current induced by white flux, and this current produces blue flux directed against our white flux from the differential current. Induction in saturatable core is low because these two flux are oriented one against the other. Current through output relay is low, nothing trips. If we have nothing trips false. If current increases, white, see difference. We have my transformer later selected. In case of if this differential current increases, current through this coil increases, and relay trips. Everything works fine. It seems on. If you assume pure sine here, this is current relay. But what happens if your primary current contains exponential component? If you have something like this, exponential component changes slowly. That means what transformation here and this transformer induced slowly changing exponential component will it's badly transformed. This blue flux will be much lesser because slowly changing exponential component will not induce EMF in this loop. Will induce small EMF. Because there will be no blue flux, this saturatable transformer will go into saturation area and induced will work as limiter. Here EMF will be much less. Because slowly changing exponential component do not produce this blue demagnetizing flux, this transformer will saturate, and this will limit sensitivity of protection. This design of relay with saturatable transformer, how to say, it protects from misoperation caused by inrush current. Key idea, it was slowly changing exponential component will not transform by this part, by right part of my free leg transformer, and will not desaturate left part. Other version of such protection is designed for limiting sensitivity as a function. How it can be done as a function of load current. Also, free leg systems used. No, this will not work for me. I need. Something like this. Saturation area. This design something like this. Operation fluxes. This is operation flux to 3. It's a secondary, in opposite direction. Primary side has an interesting setup. It has so-called braking winding. It produces flux going like this. You can use, for example, set a load current here. It produces circulating flux. And on the central core sits an operation winding for differential current. Anyone of you can arrive timing. See what happens. In this area, we have areas where braking flux comes in some with operation. Blue one tries to works to disconnect, and red one, see, if only red one circulates, nothing happens, because here it's up, here it's down for this winding, and summary induced EMF from the red one is 0. Red flux from the red winding produces no effect to operate. Blue one works to operate, but red one saturates areas where number of sheets in core is halved. The higher red one, the higher will be necessary difference in currents for relay to operate. So this design will have an interesting operation characteristic. This design will have an operation characteristic like this. Delta E, differential current. Load O, this braking current. Relay operates. Operation characteristic of such value. Operation characteristic of this one. It's a relay. It's for transformer protection. This one often used. They are still in operation for transformer protection. Relay width, differential current. Relay width. Trip point dependable on load current. If you would like, I can too much to go. modern designs are a bit different. Modern operation characteristic, because this exponential characteristic is quite, I would say, expensive in calculus burden. Modern design use bit different approach, bit simplified. Primary minus, wait a second, should be like this. Primary minus secondary differential current. And here step load current, something like this. In theory, I need to approximate non-balanced current. Modern designs usually incorporate characteristic like this, free straight line. It approximates well, and this kind of design with straight line is chosen to reduce calculation burden, to increase performance, reducing operation time. Usually it's set with two angles and two operation points. It's so-called stabilizing characteristic. For digital relays, it's actually an industry standard. Magnetic relays give smooth. They're extremely reliable. That's because they survive much longer than other models. But it is. This is street characteristic, good, in de facto industry standard, for differential protection. But this characteristic itself do not protect from misoperation due to inrush current, my yellow current. To do so, usually what's used, if we perform a Fourier analysis on this, can I perform, come here. A Fourier analysis, please, return. Yeah. Red. One. 50 hertz. Quiet. 100. 150. 200, more, 250. See what we are looking. Here is our Fourier decomposition. So idea, you can use 150. You can use combination of 100 and 250, so it will be third and fifth harmonic. What's happened? Such kind of protection do have a restricted characteristic. When M3, I prefer to call it M3, signal what we have high harmonic presence, why not odd harmonics? In case of current sensor saturation, there will be no odd harmonic. Sometimes use also 200 Hz component. can be done. But this and this one most usable. So presence of high harmony calls relay, what to relays, it shifts to restricted operation characteristic. It's a bad idea to disable protection if you observe this in our primary part. But we cannot remain on main characteristic because this current, I repeat, flows only from primary side. So we go to restricted, less sensitive characteristic. It should be selected to prevent false operation. See, they should go through Fourier filter. You need to set you will have a manufacturer advice of protection. You need to select this characteristic to prevent false operation from approximately this side, because your Fourier filter will most expected will cut this component. Your setup is something like that. But it's a problem for you. You need safe operation during inrush current. Maybe if you really need M5, what this saturation of measurement transformer also restricted characteristic should be imposed. This part mean non-balanced current during the normal load regime multiplied by 1.1. This normal operation chart adjusted to the error of your current sensors. It's approximate. Yeah, nice. But that's not all. Two problems: inrush current and error of current sensors. But that's not all. If we speak on transformer protection, star, triangle, delta, where's the problem? Current star delta, A current at delta, where will at star, where will be delta? For example, I have 11. degrees. Problem of phase shift. Transformers, real transformers, often have star delta connection, and they introduce phase shift. Transformation ratio for them is complex. Old timers used an offset current transformer connection scheme. Delta star. In such case, here current transformers would be connected in delta. here at this side. 1 second. Back. And for A. Yeah, here, offset system of current transformer connection. On the delta sides, current transformer are assembled as a normal star, but on the star side of primary transformer, current transformers are assembled in delta. Offset system, this compensates phase shift of transformer. That's not all. Can be. It's extremely, it's highly likable. What this side will have built-in current transformer with rated current 1 amp, and this lower side 5. In such case, special these are not simple current transformer built in this. Usually large power transformer comes with a set of current transformer. They are sitting where these huge insulators are going out. Below them, it's like cylinders attachment. Inside will be set of current transformers. 3, sometimes even 5. Flat current transformers. In all the schematics, interim transformers were used. Primaries assembled in delta and set of special, I don't have space, interim transformers. They will be connected in delta and they are adjustable. Interim transformers 1 to 5 amps, adjustable with adjustable transformation rate. It's done because transformation rate of this transformer is adjustable. So, in previous years, it's still very rare designs, very rare kind of new project, but sometimes this build-up with interim transformer appears. You know what appears? When there is no switch designated for transformer, it's cheaper design when transformer and its output buses is one contact of differential protection. In such designs appears this interim transformer. But nowadays it's done differently. It's done, for example, my transformer, current flow from primary sides, current from secondary side. What's done inside the relay? DFT. To perform correction into vector and matrix. It should be on one side. Matrix containing from, it has second 1, P like 6, oh sorry, A power. And what else may contain also a power, J This is rotation matrix. This matrix can be used to rotate, do not rotate, rotate to 100. This matrix ensures it can be programmed. Do not rotate, rotate with -1, and rotate forwards or backward. It's rotation matrix. This is done to compensate transformer rate. Also, on the opposite side can be done another thing. See, these large transformers are usable, have built-in ability to switch taps to the transformation rate is adjustable. It's done to control voltage. To compensate this, signal from goes to schematic to what it's to determine a real now exact transformation rate by voltage division. To compensate error caused by transformer rate. Next one. 1 omega t. 1 omega t. Omega t. What's next? Next can be operational characteristic. Very nice. And to activate restricted what's it? This one produces a free signal to activate restricted characteristic. Nice protection, but with one flaw. What kind of flaw? We have some foreign line to ground fault. Zero sequence current will flow to neutral and spread in system. This current sits only on primary side. Schematic with offset transformer is immune to this because delta connected current transformers are protecting relay from zero sequence currents. Here, zero sequence current may from it's absolutely outside fault may cause misoperation. To prevent this, we need a correction. Zero. Zero sequence current should be eliminated from the differential. BTV sequence current should be eliminated. It's one of the problem. Okay, and what's output block, and from output block this block produces these connection signals. Nice protection, but this is not enough. One more thing is done. To case switch on fault or severe damage in transformer, this characteristic can have instant show it in red. It's an instant operation characteristic where bypass pass is activated to rapid disconnect. If you have very high current difference, the instant it's an instant great characteristic. Not so simple, isn't it? May also have so it means what this need produce 5 omega currents. Sends signal M5 to go. This restricted characteristic is activated by M3 or M5. Restricted operation characteristic. Rotation 0. Small transformer protection. Small, nice, but not so sensitive as some may want. Problem. Transformer magnetic system isn't ideal symmetric. Magnetic resistance of central leg differs from side legs. One problem, another problem, steel is not ideal, transformers are not ideal, and network load isn't 100% symmetric. This limits this area, this gap is limiting. This kind of protection, it's good. It's good protection, but it's not sensitive enough. To increase sensitivity, one more operation branch can be added to increase sensitivity. I will erase part of my scheme. Another operational branch can be added. And its branch is a negative sequence differential protection. Because normal network load is symmetric, very low level of negative sequence can be observed. But internal faults in transformer introduce symmetry between legs, internal folds, because the moment is short-circuited winding produce flux oriented against the main flux. And on the peak areas, it sends the folded leg magnetized differently. This can be caged if you implement 1 omega. Negative sequence filters, they should be synchronized to prevent slide. And special, it has the same design, but much more sensitive differential characteristic for negative sequence. This will allow you to get high protection with high sensitivity. Negative sequence differential protection increases sensitivity for interwinding folds. One moment. Second, you can implement also specific thing. You can blend current transformer into ground wire. This will produce triple E0. DFT E0. Here again DFT is needed to cut third, ninth, and so harmonics. One third delta. This thing will operate on internal insulation fold winding core, or also strange, but it well works on inter winding folds. If you have fold between 110 and 10, 11, name it, winding, because there will be no balance in capacity. Also, transformer inside core with winding. It stands on something, on concrete base. Here is earthing link between transformer vessel and ground. Also, current transformer should sit here. BTV difference. If you see current here, what you will do? This relay activates fire extinguishing this. If you observe current in this earthing link, fire extinguishing system should be activated. It means internal fire. expensive protection, but high ratio transformers are expensive too. So it works. Also, of course, version for free winding or split winding transformer are available on the market. Inside the same thing. What I forgot? Something. What I need to add. I need to add something. Punkt. Debut. Okay, where am I? One second, I will add. What I forgot? Limiting sensitivity was stabilization was